Union Pacific set out to conquer the mountains with a single locomotive so massive and powerful, it weighed more than a loaded Boeing 747. It instantly condemned their own railroad. Every bridge, every stretch of rail, every turntable in its path was too weak. Most companies would have scaled back their ambitions. Instead, Union Pacific triggered a rebuild across hundreds of miles, reshaping the entire line for an engine that should have been impossible. But what drove them to this feat? And at what cost? The answer begins with a problem deep in the Wasatch Range. Freight trains crawling east out of Ogden, Utah, faced a wall of mountain that seemed to fight every ton of cargo. The Wasatch Range, stretching to Green River, Wyoming, presented grades that reached 1.14%, just steep enough to turn every run into a test of muscle and patience. For Union Pacific, moving 3,600-ton trains over this climb meant splitting the load between two locomotives, each straining in tandem just to keep the wheels turning. Dispatch logs from the late 1930s tell the story in numbers: doubled-up engines, long delays, and costly helper assignments stacking up day after day. The cost was not just measured in coal or overtime. Every time a train had to stop for a helper engine, the entire schedule shifted. Crews waited on sidings, freight sat idle, and the company burned through money and manpower. Mechanical teams watched as boilers ran near their limits, and engineers kept a wary eye on the pressure gauges, knowing that a single slip could mean hours lost on the mountain. Union Pacific's own cost sheets from the era show the scale of the problem. Double-heading two Challengers or older Mallet engines drove up maintenance bills and fuel use, while the slow pace over the grade meant fewer trains could cross the mountains each day. The railroad's ambitions for high-speed freight ran straight into the hard math of gravity and steel. By 1939, the frustration was clear. The Wasatch bottleneck was not just a nuisance, it threatened the company's ability to compete. The solution would need to break every convention in American railroading. To haul 3,600 tons at 60 miles per hour, Union Pacific needed a single locomotive with power no one had ever seen. The mandate went out: build an engine that could conquer the mountain alone and do it fast enough to change the game. Union Pacific's leadership refused to accept the limits of their mountain railroad. In 1939, a directive landed on the desks at the American Locomotive Company, ALCO, in Schenectady, New York. The message was blunt: build a single locomotive capable of hauling 3,600 tons of freight over the Wasatch Range at 60 miles per hour. No double-heading, no compromises. The engine had to do the job alone, and it had to do it fast enough to keep the railroad's schedule competitive with any in the nation. This was not a casual request. The correspondence between Omaha and Schenectady spelled out the urgency. Union Pacific's Research and Mechanical Standards Department, under Otto Jabelmann, sent calculations showing exactly what was needed: at least 135,000 pounds of starting tractive effort, enough to grab hold of a fully loaded freight and muscle it up a 1.14% grade without stalling or slipping. The boiler would need to be larger than anything in regular service. The wheels would be bigger and more numerous. Every detail pushed the boundaries of what a steam locomotive could be. ALCO's engineers understood the challenge. The company had built giants before, but nothing on this scale. The brief did not just ask for more power, it demanded a leap in design. The locomotive would have to be both massive and reliable, able to run at high speed day after day through the toughest terrain Union Pacific had to offer. Internal memos from that year show the tone. There would be no half measures. The railroad's future depended on a solution. The order from Union Pacific was clear: design a locomotive that could conquer the Wasatch Range single-handedly and do it at a speed that would rewrite the rules for American freight. The challenge now belonged to the designers at ALCO. Otto Jabelmann sat at the center of a design challenge that defied every convention in American railroading. As Union Pacific's Vice President of Research and Mechanical Design, he brought together a team of engineers from Omaha and ALCO Schenectady shops with one goal: to create a locomotive that could muscle 3,600 tons over the Wasatch Range without help and do it at 60 miles per hour. The starting point was the Challenger-type locomotive, already a formidable machine. But the numbers on Jobelman's chalkboard kept climbing. The firebox would need to cover 150 square feet, a footprint so vast it rivaled the floor space of a small apartment. Boiler pressure had to reach 300 pounds per square inch, pushing the limits of what steel and rivets could safely contain. The solution called for a new kind of articulation. Instead of the 4-6-6-4 arrangement of the Challenger, the design grew to a 4-8-8-4 arrangement with 4 pilot wheels up front, 2 sets of 8 driving wheels, and 4 trailing wheels to carry the weight of the enormous firebox. This wheel arrangement would spread the locomotive's mass across more axles, keeping the pressure on each one just within the limits that upgraded rails and bridges could handle. Diagrams from the era show engineers debating every inch and pound, searching for a balance between brute strength and practical engineering. Shop workers at Alco watched as the first engine took shape, its boiler towering above the shop floor. The scale was almost unbelievable. During final assembly in 1941, someone picked up a piece of chalk and scrawled 2 words across the smokebox door: Big Boy. No one recorded the worker's name, but the nickname stuck. It captured the mood in the shop, a mix of awe and pride at what they had built. The Big Boy was more than a machine. It was a statement that Union Pacific and its engineers would not be limited by the mountains, the rails, or even the past achievements of American steam. The numbers behind the Big Boy defy belief. From coupler to coupler, the locomotive stretched 132 feet, longer than 2 city buses parked end to end. The engine alone tipped the scales at 772,250 pounds. Add the loaded tender, and the total weight soared past 1.2 million pounds. That is heavier than a fully loaded Boeing 747. Firebox and boiler were gigantic. The firebox covered 150 square feet, big enough to roast an entire hogshead of coal at a time. Boiler pressure hit 300 pounds per square inch, feeding steam to 2 sets of 8 massive driving wheels. Each run demanded 22 tons of coal and 25,000 gallons of water. The tender rode on a 14-wheel centipede truck just to spread out the load, but raw size was only the start. The Big Boy could generate 135,375 pounds of starting tractive effort. That is the force needed to wrench a 3,600-ton freight train off the siding and up a 1.14% mountain grade without a helper engine in sight. The American Locomotive Company engineers calculated every piston stroke, every pound of steam, to make sure the locomotive could claw its way up the Wasatch Range at 60 miles per hour. In practice, crews sometimes pushed even harder, hauling over 4,200 tons on test runs between Ogden and Echo. Only 25 Big Boys were built, each one a rolling mountain of steel and fire. The scale was so extreme, it made every other locomotive on the rails look ordinary by comparison. For the first time, a single machine could do the work of 2, and do it at a speed that kept Union Pacific's freight moving on time. But with so much mass and power, the Big Boy was about to reveal a new problem. The world it was built to conquer was not ready to hold it. Civil engineers pored over maps and maintenance memos, searching for weak links along the Wasatch route. The numbers from the American Locomotive Company design sheets sent a chill through the Omaha offices. More than 1.2 million pounds, stretched across 132 feet of steel. Every bridge between Ogden and Green River became a question mark. Inspection reports warned that the heaviest spans would not survive a Big Boy crossing. Timber trestles and steel girders, once strong enough for any freight, now faced loads far above their original design. Calculations showed older bridges could yield under the strain, their supports bending with each axle that pressed down nearly 68,000 pounds. Track supervisors flagged the rail itself as a looming hazard. The standard rails, laid for lighter engines, risked buckling under the Big Boy's weight. Maintenance logs described stress fractures and spreading ties on test runs, with steel groaning in the cold Wyoming air. Even the shape of the railroad worked against the new locomotive. Sharp curves, once navigated by smaller engines with ease, threatened to bind the big boy's rigid frame. Survey crews noted that the articulated design helped, but not enough. Certain bends would force the wheels against the rail, grinding away at flanges and risking derailment. At the service depots, another problem surfaced. The turntables, vital for turning engines at the end of each run, were hopelessly undersized. Most measured 100 feet or less, built for Pacifics and Challengers. With a locomotive stretching 132 feet, crews realized the big boy would hang over both ends, unable to spin or even fit entirely on the table. Maintenance chiefs sent urgent memos. New turntables would be required, or the locomotive would be stranded at every terminal. The scale of the challenge became undeniable. Every mile of track, every bridge, every curve and depot had been built for a world that no longer fit. The big boy was ready to run, but the railroad itself was not. Union Pacific faced a stark choice: reinvent the infrastructure or let their greatest machines stand idle. Union Pacific's civil engineers faced a job that dwarfed anything they had done before. The numbers alone were daunting. Each big boy axle pressed down with 67,800 pounds, a force that could turn an ordinary bridge into scrap. Crews began by inspecting every span between Ogden and Green River, poring over bending moment diagrams and blueprints from decades past. Timber trestles and older steel bridges were flagged as bridges at risk. Some could be reinforced with new girders and bracing, but others had to be demolished and replaced entirely. Bridge contracts went out in rapid succession. Wartime priorities meant no delays. Steel, concrete, and labor flowed up the line, with teams working through snow and summer heat alike. The track itself presented another challenge. Standard rails, laid for engines half the big boy's weight, flexed and shifted under test runs. The solution was to lay heavier rail, 152 pounds per yard or more, across the entire route. Each mile demanded new ties, deeper ballast, and precision alignment. Field crews worked in sections, spiking down steel that could handle the relentless pounding of 16 massive driving wheels. Every joint had to hold, every spike driven straight, because a single weak link could derail more than just a train. The work demanded precision and endurance. At the terminals, the problem shifted from strength to scale. Most turntables on the Union Pacific measured about 100 feet, plenty for a Pacific or even a Challenger, but hopelessly short for a locomotive that stretched 132 feet. The solution was bold: install new turntables measuring 135 feet from end to end, among the largest ever built. These giants arrived in pieces and were assembled on site by teams working with jacks, cranes, and sheer determination. The first time a big boy rolled onto one of these turntables, the fit was so precise that workers joked it was like threading a needle with a steel cable. Curves along the line needed attention too. Surveyors marked out the tightest bends and calculated clearances, sometimes shifting the track by just a few feet to ensure the big boy's articulated frame could pass without binding. In some places, entire sections of rail were realigned, the ground graded and rebuilt to suit the new standard. The work transformed the route. By the time the last spike was driven and the final bridge passed inspection, Union Pacific's main line had become a showcase of heavy-duty engineering, rebuilt from the ground up to carry more than 1 million pounds of steam and steel. The track was declared ready. The big boy stood waiting, and the world's strongest railroad was about to meet its ultimate test. Big boy locomotives thundered into service in 1941, answering every demand Union Pacific had set. No longer did crews need to double up engines to conquer the Wasatch Range. Dispatchers recorded single big boys hauling up to 4,450 tons over the mountains, sometimes pushing well past their original 3,600-ton rating. Engineers and firemen learned to trust the machine's sure grip and steady pace, even as they shoveled through 22 tons of coal and burned 25,000 gallons of water on a single run. The logs from those first years show a new kind of efficiency: fewer stops, faster schedules, and a railroad that could finally keep up with the demands of wartime freight. As the war years turned into the 1950s, Union Pacific's rebuilt main line became the proving ground for these giants. Each big boy racked up more than 1 million miles, with service records listing long hauls between Ogden and Green River, then later on the broad grades of Sherman Hill between Cheyenne and Laramie. The numbers told the story. Trains grew longer, schedules tightened, and the rebuilt bridges and rails held strong. Crews wrote in their logs about the reliability of the big boys, the way they seemed to shrug off the grades that had once stalled entire trains. For nearly 2 decades, these engines were the backbone of Union Pacific's mountain operations. But the world of railroading was changing fast. Diesel locomotives arrived with lighter frames, lower maintenance costs, and the promise of even greater efficiency. They did not need massive turntables or constant coal and water stops. By the late 1950s, the economic advantage was clear. On July 21, 1959, the last big boy made its final revenue run, quietly ending an era that had lasted less than 20 years. By 1962, all 25 were officially retired. For most steam giants, the end meant the scrapyard. Yet something about the big boy's scale and legacy inspired a different fate. 8 locomotives escaped the torch, preserved in museums from Cheyenne to Dallas. In 2013, Union Pacific reclaimed locomotive 4014 from a California museum, hauling it back to Cheyenne for a painstaking restoration. After nearly 6 years of work, Locomotive 4014 steamed under its own power again in 2019, a living reminder of the ambition and the upheaval that once reshaped an entire railroad. Today, it stands as proof that even the most impractical dreams can leave a mark that endures long after the world has moved on. Today, the scars and reinforcements along Union Pacific's routes still echo one truth. Sometimes, ambition reshapes the world itself. As infrastructure faces new pressures, heavier trains, and climate extremes, we confront the same question. Do we adapt our ambitions or force the world to adapt to us? The legacy of Big Boy reminds us that progress always leaves a footprint. What kind of mark will we choose to make next?